Hey guys, for the last two videos we've been talking about inferences on proportions. Now we're finally going into the other half of hypothesis tests and confidence intervals, which is on means. Just a review of a mean sampling distribution. No matter what shape the parent population is, it could be normal, it could be skewed, or it could be uniform like here. If we keep taking samples out of the parent population and then averaging the numbers we get from the parent population, we will end up with a normal distribution, and this is the sampling distribution that we will work with. So the kind of place that you will need to do inferences on means is for situations like this. So let's say the mean weight for American cows is 1,309 pounds with a standard deviation of 157 pounds. We take 100 cows at a time and find their mean weight. What is the standard deviation of the sampling distribution? Or I could also ask you to make a confidence interval or do a hypothesis test on this scenario. So one thing that you really need to remember is that even though we're given a standard deviation up here, this is not equal to our sampling distribution's standard deviation. So even if the parent population is already in a normal distribution, let's say it looks like that, if we take samples out from this parent population, because we're averaging the samples that we get out, we're going to have less variation from sample to sample. So therefore, our sampling distribution will look something like this. You can immediately tell that this model is much skinnier than its parent model, and this thus shows that we have a smaller standard deviation for our sampling distribution. So it doesn't matter what the standard deviation of our parent population is, our sampling distribution will have a different standard deviation. So try not to get those two mixed up. We have some different important numbers now. So now we have an X bar to deal with. This is sort of equivalent to our p hat for proportions in terms of what it symbolizes. This is our sample mean. And for proportion tests, the number that we made inferences about was our p, or our population proportion. Our population mean now is going to be our mu. Our n is still the same, that's still our sample size, but the way we calculate our standard error has changed a little bit. Because now, we're not working with proportions anymore, so our old formula of the square root of pq over n does not apply anymore. The new formula is equal to our population standard deviation divided by the square root of n. So the sigma is the population standard deviation, and it's used to calculate the sampling distribution's standard deviation. So you always have to divide by the square root of n before you start your problem. This is a really easy thing to forget to do. Next we have a new number called our degrees of freedom, or df. I will go into what this is used for in a minute, but for now all you need to know is that your df for a problem is equal to your n minus 1. So your sample size minus 1 is equal to df. By the way, df is not a number d times a number f. df is just an abbreviation for degrees of freedom. It's one term. Next we have our t sub df. So this is taking the place of our z-scores from proportions, but this one is specially used for questions about means. And this df has a big factor in determining the t, which is why we put it as a subscript. So if our df was equal to 3, for example, we would write it as t sub 3. So where all of this df stuff and the t stuff comes in is here. So for our t distribution on means. The reason we have our degrees of freedom and our t-scores and all that stuff is because for inferences about means, we're not using the normal model anymore. We're using a t-model or a t-distribution. So for proportions, everything was centered around z-scores and then making inferences based on the normal model. Now we have to draw t-models. So this is very similar to a normal distribution. It's still a unimodal and symmetric shape, but its properties are a little bit different. So here is our normal distribution. This is the one that we're used to seeing. And then in comparison, here is a t-distribution. At first glance, they do look practically the same, but you will notice here at the tails, it is much fatter than our normal distribution, and it does not go as high. It does not peak as much as the normal distribution. As far as we've learned, the normal distribution is determined by a mean value and a standard deviation. So that's why we always notated it as n and then mu and sigma. All you need to describe a normal distribution is a mu and a sigma. For a t-distribution, there is no mu or sigma, to define it, it is defined with a number called the degrees of freedom. So the number of the degrees of freedom determines the shape of the t-distribution. So if there are 5 degrees of freedom, it has less of a peak and it's fatter here. However, as you increase the degrees of freedom, it starts to cluster more towards the center, its tail becomes smaller, and it peaks more. As you increase your degrees of freedom, your t-distribution starts to look more and more like a normal distribution. And the thing with our t-value up here, this can also be called a t-score. And the way we calculate it is the same as for a z-score, but instead we're starting to find values on the t-models corresponding to the number of degrees of freedom. So if the degrees of freedom for our question is 34, then we would take this model and then we would calculate a t-score on here to use to solve the problem. Because all of our old calculator functions were dealing with normal model, for example, norm CDF or inverse norm, we have to have some new ones for the t-distribution. So here, the names are very similar. We have the inverse t, which is notated like this, inverse t. The stuff that you put into the calculator is basically the same as the inverse norm. So your inverse norm function is used to find your z-critical values. Therefore, your inverse t function is used to find your t-critical values. So what it takes in is the area that you're looking for and the degrees of freedom. In contrast, our inverse norm function took in an area that was the same, but it took in a mu as well and a sigma. So these are used to define what model we're using, but the area that you're putting in is still calculated the same way. So if you wanted to get a 95% confidence interval for a t model, that means that you want 95% in the middle, and you still want this number over here. So you would want everything from negative infinity up to this wall, meaning that you have to add on the extra 2.5% here. Because still, the t model is also perfectly symmetric. So the area you would put into the calculator for your inverse t function is 0.975, and all you need to put in is your degrees of freedom. So if we have 10 degrees of freedom, then you would just put in 10, and then you would get back out some t-critical value. Next we have our t-CDF function. What it does is basically the same as the norm CDF function. It takes a lower bound and an upper bound, and it gives you back out an area. So again, contrasting what they take in, our t-CDF needs the lower bound, upper bound, and degrees of freedom. Our norm CDF takes in lower bound, upper bound, mu, and sigma. For example, if you're doing a hypothesis test, for norm CDF you would put your z-score into one of these two and then infinity or negative infinity into the other one. And then you would use this to define what kind of model we're working with, so probably the standard normal model. But for our t-CDF function, we would put in our t-score into either the lower and upper bound and then positive or negative infinity into the other one, based on which direction our test is going in. And then we put in our degrees of freedom again to define which kind of t model we are going with. They basically serve the same function in mean hypothesis test and proportion hypothesis test. They're both used to find our p-value. So first we have our confidence intervals. This concept is basically going to be the same again. So we have some center x bar value, so our sample mean as the center of our interval, and then we stretch out our arms by some margin of error. The way we calculate our margin of error has changed a little bit, but the background concept is still the same. So our margin of error can be expanded outwards into a t-critical value now times a standard error. For proportion confidence intervals, it was z-critical times a standard error. Now, because we're talking about means, we have a t-critical times a standard error. Now our standard error is equal to now sigma over the square root of n. Putting that into practice, we have a question here. The standard deviation of the weight of all American cows is 157 pounds. We take 100 cows at a time and get a mean weight of 1,298 pounds. Create a 95% confidence interval for the true population mean weight of all American cows. I should have put the word weight in there. So we need all of these important numbers to make our confidence interval. The first thing we need is the center of our interval. That is our sample mean. So when we went and sampled the weights of the cows, what did we get for the mean weight for our sample? It says up here that we got a mean weight of 1,298 pounds, so that is our x bar. Next we need a sigma. So this is our standard deviation for the population, and it is apart from our sampling distribution's standard deviation. It says up here that the standard deviation for all American cows is 157 pounds. Because it says all, that means that this is our population standard deviation, so 157. Next, we need to calculate our standard error. So our standard error is equal to sigma over the square root of n. We have sigma up here, but we also need n. So n is the size of the sample that we took. It says we took 100 cows, so that means our n is 100, and we can calculate our standard error now, which is equal to, plugging everything in, 157 over the square root of 100, and that is equal to 15.7. Finally, we have almost everything we need. We just need our t-critical value. So to get our t-critical, we use our calculator function inverse t. We put in an area and a degrees of freedom. So what is our degrees of freedom equal to? Degrees of freedom is always equal to n minus 1. And what is our n? 100. So 100 minus 1 is equal to our degrees of freedom, and that is 99. So our t-critical sub 99, note you always put the degrees of freedom as the subscript for your t whatever, whether it be your t-critical or your t-score. So we know that our degrees of freedom is 99, we just need an area as well. So looking at a t-model, again, it doesn't have to be perfect. We put 95% in the middle. That is the confidence level that we want, and we want this number over here. So going from negative infinity to this number, that means we have 5% left outside and 2.5% left on this side and 2.5% on this side. Putting that together, everything on this side is 97.5%. So our area is 0.975. And our t-critical value, now that we have everything we need for the calculator, is 1.984. So we have everything we need now. Let's make a confidence interval. So we plug everything in. Our x bar is 1,298 plus or minus our t-critical of 1.984 times our standard error of 15.7. Doing all the math for that, our final interval is 1,266.85 and 1,329.15. So what does this interval mean? So our original thing was to see the weights of cows, right? The mean weights of cows if we took samples of 100 at a time. And we're using it to make an estimate about the mean weight of all American cows. So that means that our interval is an estimate for the mean weight of all American cows. Therefore, we can say, I am 95% confident that the mean weight of all American cows is between 1,266.85 pounds and 1,329.15 pounds. So in order to create our confidence interval in the first place, or to run a hypothesis test, we need to satisfy these four conditions. These three are still the same: independence, randomization, and 10%. So the weight of one cow should not affect the weight of another. The cows were randomly selected, and then we sampled under 10% of all American cows. Our large enough condition has changed. So for proportions, our large enough condition was in the form of the success-failure condition. For means, we have the nearly normal condition. So this one depends only on our n, so our sample size. There is no p or q to consider now. So what it says is that if n, so your sample size, is greater than 30, you don't have to worry about anything else, you can proceed, everything is fine. This is always what we want to do because it saves us a lot of time writing. Our next one says that if your sample size is between 15 and 30, the sample must be unimodal and symmetric. This rule is kind of bendable. As long as your sample just looks unimodal and there's no clear outliers or anything, you're basically good to go. When you have a sample size about this big, problems will generally give you a data table. What it's going to say is that we got 20 cows and then we took the mean weight of them, but just so you can satisfy your conditions, we're going to give you the individual weights of each cow. So even though your x bar is already given, let's say it's like 1,000, they will still give you the individual weight of each cow that they sampled to create that mean. So you can use those numbers for each cow and create a histogram of the weights of every individual cow to see if it's unimodal and symmetric. And finally, if your sample size is under 15, then your population has to be strictly normal. That means that the original distribution has to be a normal model. For example, if we only sampled 10 cows, then that means that in order to create a confidence interval, the weights of all American cows has to follow a normal distribution. The most critical thing to remember here is that anything that is a natural phenomena is likely going to be in a normal distribution. Again, the weights of cows, the weights of people, or the heights of people, the length of cats, all of these are natural phenomena, and therefore they will follow a normal model. So here are the steps for a hypothesis test. The first thing that you have to do is to list out what you're interested in finding. So let's say I am interested in finding if the cows on this farm are really undernourished or something. This is what your ultimate goal is in context. Then you list out your important numbers. So what are my hypotheses? What is my alpha value? What is my x bar, my n? You have to give degrees of freedom, your standard error, your sigma, etc. Then you do your conditions. So we just went over them. Those are your independence, randomization, 10%, and large enough condition. Then you calculate your t-score. So your t-score is going to be written like this. Your t sub df is equal to your x bar minus whatever assumption you made in your null hypothesis. So your hypotheses will look something like this. Mu is equal to some number x, and then your alternative will be either mu is not equal to, less than, or greater than that same number. So then the number that you put into your t-score will just be this x value, your original assumption, and then you divide it all by your standard error for x bar. So this is again equal to your sigma over the square root of n. Now that you have your t-score, you draw a t-model. It doesn't have to be perfect. If you draw a normal model, it really doesn't matter because they look so similar anyways. So you just draw your t-model, and then you flag your t-score and shade in the area from your t-score to the nearest extreme. Then you use your calculator's tcdf function to get a p-value. And with that p-value, you can conclude. So because we have so many different kinds of tests that we've gone over now, we've done a 1 proportion, a 2 proportion, and now we have a 1 mean test. There are so many different names for it, and so this is just to help you review and make sure you don't mess this up whenever you're naming the test that you're going to do. Whenever you do a confidence interval and you finish up your conditions, you will always have to give a concluding sentence, right? No matter whether you're doing an interval or a test. The first 2 things that you name is always 1, the number of samples you have, so 1 or 2 samples, and then you say proportion or mean. The name of the next part is the most important part. So if you're doing a confidence interval, the name of what you're going to be doing is always going to be interval. So if you're doing a 1 proportion confidence interval, then it's going to be 1 prop interval. If it's a 1 mean confidence interval, then it is a 1 mean interval. You'll notice that there are letters in front of these. So if you're working with proportions, then you always use the letter z, because everything depends on your z-scores or your z-critical values, and because for proportions, you work with a normal model, and for normal models, you always use z. For means, on the other hand, you will be using the letter t, because means are based off of a t distribution. The same rule also applies for hypothesis tests. So in this case, instead of interval, we use the word test, and then if we're working with proportions, we use z. If we're working with means, we use t. In this case, we are about to do hypothesis tests on a 1 sample mean. So we will be doing a 1 mean t-test. Spoiler alert, since we have a 1 proportion z-test, a 2 proportion z-test, a 1 mean t-test, then you can probably guess that the next video is going to be over 2 mean t-tests. But I get ahead of myself. So here's the question. The mean weight for American cows is 1,309 pounds with a standard deviation of 157 pounds. We take 100 cows at a ranch and take their mean weight, getting 1,200 pounds. Are the cows on this ranch abnormally light? So the first thing we say is what we're interested in. So in context, what are we interested in finding out? So we are going to say, we are interested in finding if the cows on this ranch are abnormally light. We basically just repeat the question so that people know that we know what we're doing. Next, we can go on to step 2 and list out our important numbers and our hypotheses. So first, I like to go with the important numbers. First of all, I will give my sample mean. So what did we get from sampling the cows on this ranch? We got 1,200 pounds. So that is our x bar. Our n, so our sample size, needs to be given as well. That's how many cows we looked at. So we looked at 100 cows. Our sigma also needs to be given, so that is our population standard deviation. So that is 157 pounds. We don't need to put the standard error just yet. That can go into step 3 when we calculate our t-score, but you can put it if you want. I personally prefer to have it with the t-score calculations. So therefore, we only have one thing left to put, and that is our degrees of freedom. So that is equal to n minus 1, so 100 minus 1, which is 99. Now our hypotheses. So our null hypothesis is going to be that nothing weird is going on in this ranch. We maintain the status quo. So therefore, our null hypothesis is that our mu, so our mean weight of all cows on this ranch, is going to be equal to the population mean, so 1,309. Nothing weird going on here. Our alternative hypothesis is that the cows on this ranch are abnormally light. So that means our mu, so the mean weight of cows on this ranch, is less than 1,309. Note that this time we have been given a direction because the question said abnormally light, not is the weight different from the population mean. And then finally we give our alpha threshold value, still 0.05. Next we have our conditions. So first, does the weight of one cow affect the weight of another cow? No. The question does not say the sample was random, so we have to give our weird statement here that although we don't have any reason to believe that the sample is randomly taken or representative of the population, we also don't have evidence to believe that it is not representative. 100 cows is surely less than all cows in America, so we can just say that the 10% condition has been satisfied. And because our sample size, which is 100, is way greater than 30, our large enough condition, or nearly normal condition, is also satisfied. And because our conditions are satisfied, we can proceed with A and then name our test. So a one mean t-test. You can write this one of two ways actually. You can say either one mean t-test or one sample t-test. I personally use one sample, but one mean also works as well if you want to be more specific about what's going on. So our next step is to get that t-score. So in order to get our t-score, we need our x-bar, our mu, so whatever this is, 1,309, and then we need a standard error. So let's get that standard error first. So the standard error of x-bar is equal to sigma over the square root of n. We have sigma. Sigma is equal to 157 as given in the problem, and then n is 100. So our standard deviation or standard error for the sampling distribution is 15.7 pounds. Using this, we can now get our t-score. So our t sub 99 for degrees of freedom is equal to x bar, so 1,200, minus our original assumption in the null hypothesis, 1,309, over our standard deviation of 15.7. And that is equal to negative 6.815. So that's our t-score, and then we can use this to draw our t-model. So you come over here, we draw something that looks approximately unimodal and symmetric. So we start from 0 and move in the direction that we need. So 0, negative 1. So negative 6.8 is probably somewhere around here. And then we move towards the nearest extreme. So that would be towards negative infinity. And then we label negative 6.815. So this is the area that we're interested in finding. Next, we use our calculator in step 5. So the probability that our t-score goes under negative 6.815 is equal to, and then we put in our calculator language. Note that this time I did not multiply it by 2 because our alternative hypothesis only says less than. If it said not equal to, I will multiply by 2, but this time it doesn't, so I don't need it. And then we put in our calculator function. So this is tcdf, and we give a lower bound, an upper bound, and a degrees of freedom. So we know our degrees of freedom already, that's the easiest one, 99. And then we have to put in a lower bound and an upper bound. So the range that we're interested in is from negative infinity to our t-score. So our lower bound would be negative infinity, and our upper bound would be our t-score of negative 6.815. Putting that into the calculator, we get an incredibly small number. It came out in E notation actually, but if you want it as an actual decimal, it looks like 0.1234567893724. That's our p-value. You already know straight off the bat that we're rejecting our null here. This is way too small of a probability. So we can conclude with this p-value. So if the mean weight of all cows on this ranch is truly equal to 1,309, the probability of the observed data occurring would be 0.00000003724. Because the p-value is so small, don't make me repeat that number. It's less than alpha, which is equal to 0.05. I reject the null. So that is your one sample t-test. Again, this should really start to look familiar because we'll basically be following the same template for the rest of the course on hypothesis tests and confidence intervals. You're almost there. Thanks for watching. Hope you learned something. Peace.